so this is 2016 Mechanics C, question 1. Motion-centered cart. Okay, cart of mass m is pulled along. This could be work. This could be kinematics. This could be just calculus. We'll find out. A force sensor is attached with a string used to measure the horizontal force of the cart. Motion sensor measures the acceleration. Positive is to the right, so they've made that declaration for us. On the dot below, label the forces, not components. We talked about that at ADC, but we don't have to care about there on the cart. Great, so there's got to be friction involved, yes? All right, friction is not negligible, very specific. So here we go, Fn, Fg, Fk, opposite the motion, and F applied, okay? Great, ooh, 3 points for us. A student pulls the force sensor with a constant force and the car accelerates. This is repeated for several trials. With a different constant force used for each trial, the data is recorded below. Okay. On the graph, plot data points for the acceleration of the cart as a function of the force sensor reading. Oh, so like we don't have to do anything. We just got to plot it. All right. So this goes, my data goes up to 0.6. So 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. This is really a waste of everyone's time. 0.1, actually no, this goes up to 0.7, so I got to do 0.15, 0.3, 0.4, 0.5, 0.45, 0.6, 0.75. Just I want to use as much of the graph as possible. So when the force is 3.2, okay, the reading is 1.12, okay. When the reading is 3.8, the way they presented this data is just wretched. It is there. When it is 0.44, okay, I've got 0.33. Yep, okay. 0.5, okay, 0.6 is the force sensor reading, 0.70, boom, okay, there we go. Using the straight line from the graph, calculate the mass of the car, draw a straight line, okay. All right, from the straight line, calculate the mass of the cart, okay. Oh, this is just annoying. So here, because we know F net is equal to MA, right? But the slope here is A over F. So the slope here is 1 over the mass. Like, come on, just flip-flop it. That's just, I know, like, you're supposed to put the thing you're choosing to be here and whatever, but sometimes, you know, a real experimentalist is just going to flip-flop things around just so they don't have to deal with it. Great, so let's calculate the slope of this thing. I conveniently put through 2 of the data points so I can use them. It actually makes a pretty nice best fit line. So 0.7 newtons, 0.7 meters per second squared over 0.6 newtons. And then this one was the second data point. So minus 0.22 meters per second squared minus 0.38 newtons. And so the slope here is 0.7 minus 0.22 divided by 0.6 minus 0.38. By the way, I'm really hungry, so if I'm being ornery, that's probably the reason why. Yeah, let's chalk that up to be the reason why. Anyway, meters over second squared divided newtons, that's 1 over kilograms. So that's 1 over the mass. So the mass is just going to be the inverse of that. So 0.46 kilograms. Done. From the straight line of the graph, measure the magnitude of the force of friction. Okay, so in other words, now that I know that mass, we can go back here. I'm actually going to go to a separate sheet of paper because we know that F net equals ma, and so the applied force minus the frictional force is equal to ma. Now we know what A is, so I can just use any of the data points. So I'll use the last data point. When the applied force was 0.6 newtons minus Fk, we had a mass of 0.46 kilograms and an acceleration of 0.7 meters per second squared. And so now I can do 0.46 times 0.7, okay, minus plus 0.6. Fk is 0.278 newtons. Okay, good, so that's that. The time above experiments repeated using a constant force scale reading of 0.45. So in other words, that's here. The cart starts from rest at time 0 and is pulled for a time of 2 seconds. Determine the acceleration of the cart. Okay. Okay. So I can just interpolate. Right. So that's just okay. Okay. And so CI, my interpolation is 0.375 meters per second by interpolation. Okay, the string breaks at t equals 2 seconds. Calculate the time for the car to stop after the string breaks. Okay, cool. I need to know what the speed is at the end of that. So let's figure this out. So I know that that's the acceleration. And so let's find VF in this interval. So II. So what I'm going to do here is do VF in that interval, and then I'm actually going to use impulse momentum theorem in order to figure out the time. I could find out a new negative acceleration and do more kinematics, but I think this is going to be a more convenient solution. So I know it started at rest. VF in that first interval is 0.375 meters per second squared. The time is 2 seconds. How convenient, 0.75 meters per second. Great, so that's how fast it's going. And then I know delta P is equal to F net, or the sum of forces, delta T. That's my impulse momentum theorem. Now I know the frictional force here is 0.278 newtons. It is a -1. I'm looking for what this delta T is. And so delta P is PF minus PI. We know it's going to come to rest. That's the whole point. So negative, we know the mass of this thing is 0.46 kilograms. We just found out this is moving 0.75 meters per second, is equal to negative 0.278. Boom. Right. By the way, this using impulse momentum theorem to find out how long it takes how long it takes for a change to occur is actually really helpful. In the same way, if I wanted to know how far it went, I'd probably use the work energy theorem. Okay. So 0.46 times 0.75 divided by 0.278. Boom. And so the delta T, the time period over which this occurs, is 1.24 seconds. Great. Experiment analysis and A and B are repeated with a cart that has the same mass but a greater force of friction. Will the slope of your new line be greater than, less than, or equal to the slope of your line for part B? Okay. With a horizontal intercept of your new line. Oh, that's stupid of me. I should have totally realized I could have done that. Right? So in other words, that there's your force of friction, which I was pretty spot on with that one. That's pretty good. So we know that the force of friction is going to be greater. So that means the force of friction is the horizontal intercept. So the horizontal intercept, we don't have to explain. So the horizontal intercept's greater. Now, would the slopes change? Well, let's see. With the same force, we're going to get a smaller acceleration, right? Because there's the net force is going to be smaller. So the slope is going to, therefore, if the force sensors are going to remain the same, all these points retract downwards, it's going to be less than. I don't have to explain. So there we go. That's that problem.